Welcome back to our ongoing discussions of how light interacts with matter. I last time began to introduce you guys to some of the basic foundations of quantum mechanics that we really need to mechanistically understand that process. Right? So if you remember where I left you the last time, I wrote down the Schrodinger equation for you guys, which looked something like this, which is that Hamiltonian operator applied to a wave function, right, is equal to, or the impact of the Hamiltonian to a wave function for a system that we happen to be interested in is equivalent to the application of the quantum mechanical energy operator, all right, which was this I times Planck's constant. I, of course, is that imaginary, fundamental imaginary number, square root of -1. H bar, again, being Planck's constant divided by 2 pi, times the partial derivative of that wave function for that system we're interested in with respect to time, right? Now, again, just reminding you guys that, of course, that Hamiltonian is equal to that sum of a quantum mechanical kinetic energy operator and potential energy operator. We're going to come back to that in a minute. Now, the way that equation is written, it's dependent on time. And the reason it's dependent on time, or as a function of time, is because in this equation, the wave function is, of course, a function of time, right? And so when the Schrodinger equation written this way is sometimes referred to as the time-dependent Schrodinger equation, right? Okay, because the wave function is a function of time, that the operator is assumed to be a function of time, right? Okay, now the way you would normally use the Schrodinger equation, of course, is to find this wave function. Remember, our goal here is to be able to apply operators like this Hamiltonian or some other operator that is linked to a physical observable or something we want to know about a system to get a measurement out or to predict a certain behavior, right? To learn something about that system. But for that to work, you have to have the wave function. If you don't know the wave function, all of this is more or less meaningless, right? So the Schrodinger equation, of course, comes to the rescue of that problem of what is the wave function for a given system, because if you know your Hamiltonian, that's well specified. You can apply that Hamiltonian with some other knowledge of the system to solve what here is this relatively, at least as is written out, simple looking partial differential equation of the Schrodinger equation, right? If you could solve that in principle, you can get the wave function. You can specify the wave function by just solving the Schrodinger equation, right? Okay, that sounds straightforward for the most part. Turns out it's not, right? Well, or I should say, it's relatively easy for simple systems, right? And it can be solved exactly for simple systems. For example, a free particle in space, simple atoms like the hydrogen atom. You can solve for a complete version of Schrodinger, the wave function for that system. For most other more complex systems, like for example, the wave function of a protein in solution, water or whatever, is vastly more complex. And we don't have any real clue how to solve for a complete version of the wave function of a system like that. The best we can usually do is come up with approximations. In some cases, exact solutions may not even be possible. In other cases, we just may not even we don't have the math yet to know how to do it. And so usually approximations are necessary to find those wave functions for more complex systems. But it turns out, all right, that if an operator, just mathematically, it turns out that if an operator that one was interested in is independent of time, right? That if you have, say, like I said, some operator here, we'll just call it P, that is independent of time. Right, so it doesn't depend on time in any way, right? And if that operator is also an eigenfunction of, or I should say, if a given wave function for a system one cared about is an eigenfunction of that time independent operator, something kind of interesting turns out to be true. And what turns out to be true is that the system that described by that wave function is, if it's an eigenfunction, right? I should say, let me write this out. If the wave function of this system is an eigenfunction of that operator, then what turns out to be true is that this system is in essentially a stationary state with respect to that operator, right? It doesn't change the function of time. And even more amazing, what turns out to be true, is that the energy associated with a system like this, that is an eigenfunction of a time invariant operator, turns out its energy is not continuous, it's quantized, right? And to see how that works, let's turn back to an operator we would in principle care about, which in principle is the Hamiltonian, right? So let's go back to that Hamiltonian operator, right, which of course we can write out with that symbol H with a hat on it. And again, we're going to assume that it's independent of time. So we're going to assume we have a Hamiltonian that's independent of time. Which means we can write it this way. We have our Hamiltonian little hat. Remember, it's an operator, but it's only a function of the position of the particles, the components of our system. It's only a function of spatial orientation, right? Or positioning of the components of the system. Now, if that's true, right? And if we have a wave function of this time invariant Hamiltonian for a system, that happens to be an eigenfunction of that time invariant Hamiltonian, which in this case would mean applying the Hamiltonian just returns the wave function times its energy, right? If that's true, right, then it turns out that it's actually trivial to specify the time dependence of that wave function in the following way. Because if this is true, we also know that the following has to be true based upon the Schrodinger equation here, right, where the Hamiltonian times the wave function is equal to the quantum mechanical energy operator applied to the wave function. Excuse me, the quantum mechanical energy operator applied to the wave function, so it's partial derivative in time. Because we're going to just be working with time, we're going to assume all of the variables are basically not going to be a variable. We're not going to have to worry about partial differentiating them. In this case, we can just shift back to normal differential notation, so that if this is the case, what also has to be true is that this would have to be equal to I h bar times the derivative of the wave function with respect to time, right? That's more or less just a straight off truism from the Schrodinger equation, which we've assumed to be shown to be true. Okay, so I'm going to write that out a slightly different way here. And again, that is, I'm going to just rewrite that expression, which is the derivative if we have a time invariant Hamiltonian that is an eigenfunction of this wave function, right? Then the derivative of that wave function with respect to time times h bar and I is simply equal to its energy times the wave function. Okay, so what we have there is a relatively simple, a really fairly simple, ordinary differential equation in this case, in a single variable, right? Now you guys may or may not remember your basic differential equations or how to solve this. I'm going to solve one for you explicitly when we talk about simple chemical kinetics here in a little while. That it has exactly the same mathematical form, but this time I'm just going to give you the answer. The solution to that equation is really fairly simple. It looks like this. The time dependence then of that wave function, so psi as a function of time, is simply equal to the value of the wave function at time 0, all right, times e to the minus, that's e, the exponential function, e to the minus I, it's capital E, that's the energy of a system, times t divided by h bar, right? Now that's kind of cool, because what that means, I can write this in a slightly different way. Right? What that means is that the time dependence of that wave function is simply equal to a constant times this exponential decaying function of time multiplied by energy, and it's got this imaginary component to it, right? But it lets me rewrite the amplitude of that function with the lowercase psi. That's what people usually shift to, which means that because we're talking about the sort of amplitude part of this decay here, the pre-exponential component, it doesn't depend on time, right? It's at time 0, which means the amplitude of this exponential function only depends upon the coordinate positioning of the particles of the system. It's not a function of time, which then generally gets rewritten this way, where we shift to a lowercase psi, and now it's the wave function is only a function of the positional coordinates of the system. It's not a function of time anymore. But the time dependence now is all in this exponential part, right? That's kind of cool, because what that means is if that's the description of our wave function, remember, this is a wave function that satisfies this condition, right? It is an eigenfunction of this time invariant Hamiltonian. What it means is the following. If that's the answer, you can take this expression, plug it back in to the Schrodinger equation, right? The time-dependent Schrodinger equation, and what you get out, I'm not going to do it for you. So if you substitute into the time-dependent, you're welcome to do it. It's not hard. It's like 2 steps, but time-dependent Schrodinger equation, and you solve, what you'll find, or what you find out, is that the following equation sort of drops out, which is that time invariant Hamiltonian times that time invariant wave function, right, is simply equal to E times the time invariant wave function, which means that the time invariant wave function of this system is an eigenfunction of that time invariant Hamiltonian, right? So application just returns the energy. This is a sort of a general solution to the Schrodinger equation under a special set of conditions, and it gets a name. This is known as the time independent Schrodinger equation, right? Okay, it's going to become useful to apply this, right? Okay.